Hello everyone, this is the summary video for the distance formula, and we are going to cover three things in this video. I am going to do the derivation of the distance formula, like we did in class. And then I'm going to do two examples, one that's pretty straightforward. You'll see one just like this in your homework assignment, and then one that is probably the most challenging homework question that you will see. So it's an example that's similar to it. This video will probably be a little bit long, but remember in your notes you have the times for when the end of one of those three parts ends. So, if there's a specific thing that you want to see, you can refer back to your notes and see what times those things happen in the videos, and then you can skip to them. So, all right, let's get this started. So in class, we derived the distance formula from the Pythagorean theorem. So remember that a derivation means we are starting with the Pythagorean theorem and then we are changing it until we get to a new form. And that new formula really gives us the distance formula. So let's do the derivation. So suppose that A is at the coordinate x sub 1, y sub 1, and B is at the coordinate x sub 2, y sub 2. Use the same procedure for number 6 to find the length of AB. So remember that we were using the Pythagorean theorem, and in order to use the Pythagorean theorem, we have to turn our triangle or our segment into a right triangle. And if our triangle is right, let's call this point C, then we can, and that's side C because it's opposite, and this is side A because it's opposite of vertex A, and this is side B. Then we can say by the Pythagorean theorem that a squared plus b squared is equal to c squared, as long as our triangle is right. So what we want to do is change a, b, and c into expressions, and then we're going to solve for c. So remember in our prerequisite video for this segment A that we're really talking about a change in y here. So to express a change in y, let me back up there for a second. First, we need to find the coordinates of C. So C is as far over left or right. It has the same x coordinate as B. So the coordinate here is x sub 2. And then the y coordinate is as high up as A. So then the y coordinate is y sub 1. So it's as far over as B and as far up as A. So the coordinate for C is x sub 2, y sub 1. Okay, back to finding A. So remember that finding that length is really the change in y. So to find the change in y, we just need to subtract them. And we can say that A is equal to y sub 1 minus y sub 2. But really, remember we need the absolute value to account for any negatives. Okay, and then for B, we can say that B is the change in x. So this is a delta x, a change in x. So B is equal to x sub 1 minus x sub 2. And then we're going to put that in absolute value as well. So then we're going to use those expressions and substitute into our equation over here. So a squared becomes the absolute value of y sub 1 minus y sub 2, and then we're going to square that absolute value. Okay, and then we're going to substitute in for b. So we've got plus b squared, and b squared becomes the absolute value of x sub 1 minus x sub 2. And we need to square b because it's b squared. All right, and all of this is equal to c squared. Okay, now if we think about this algebraically, even if this number is negative and we don't take the absolute value of it, as soon as we square it, okay, it takes care of the negative issue of distance. So we actually can get rid of the absolute value because we're squaring these quantities. So we can simplify this to y sub 1 minus y sub 2 quantity squared plus x sub 1 minus x sub 2 quantity squared. And all of this is equal to c squared. Well, c squared is the distance between AB. And really, we can rewrite that as the segment AB squared is equal to y sub 1 minus y sub 2 quantity squared. So the difference, the change in our y, plus the change in our x squared. X sub 1 minus x sub 2 quantity squared. Okay, so to finish this up, our goal is to solve for just AB. And if this is AB squared, then we can square root both sides and simplify this. So we're going to square root this side, square root this side. Okay, now there's nothing that we can do with the left side of this. So it is going to remain as the square root of y sub 1 minus y sub 2 quantity squared plus x sub 1 minus x sub 2 quantity squared. Okay, and we can't simplify those squares because of this plus sign in here. Okay, so that is really, really important that we cannot take the square root of those because they have to be added together first. Okay, but this is all equal to, we can take the square root of AB quantity squared. So this is all equal to AB. So now, oops, if we just kind of reorganize this, we can say that the segment length of AB is equal to, and we'll put our x coordinates first, x sub 1 minus x sub 2 quantity squared plus y sub 1 minus y sub 2 quantity squared. And there it is. That is the distance formula. If you want to generalize this to be the distance of any segment, just not a segment of AB, which is probably a better idea, then we call it D for distance. Okay, so that is the derivation. So moving from the Pythagorean theorem, finding those segment lengths, substituting them in, and then solving for D, your distance. All right, let's take a look at some examples that apply this. So the first one says the endpoints of two segments are given. Find each segment length and tell whether the segments are congruent. If so, write a congruency statement. So we are going to find the segment length of segment AB. And so we're going to apply the distance formula. I'm just going to put it up here. It is the change in our x's, quantity squared, plus the change in our y's, quantity squared, all underneath a radical. So in AB, if we call this x sub 1, y sub 1, and x sub 2, y sub 2, we can apply this into the formula. So AB is equal to the square root of, well, we're going to substitute in our x's. So 0 minus 9 quantity squared plus the change in our y's, negative 4 minus negative 1 quantity squared. Then you need to use your order of operations and simplify this. So AB is equal to the square root of 0 minus 9 is negative 9, but negative 9 squared is 81, plus negative 4, a minus a negative becomes a positive, so negative 4 plus 1 is negative 3, and negative 3 squared is a positive 9. So AB is equal to the square root of 90. And we can simplify that. We can take out a 90, it factors to 9 and 10, and the square root of 9 is 3. So 3 root 10. Now we're going to find the distance of segment CD. So if we call this one x sub, we could call it like 3 and 4. Like that's really better because we already have an x sub 1 and an x sub 2. So, and still we're going to do the same process. So CD is equal to the square root of, we're going to subtract our x's. So find our difference. 12 minus 9 quantity squared plus 1 minus 10 quantity squared. So CD is equal to, we're going to use order of operations. 12 minus 9 is 3. 3 squared is 9. plus 1 minus 10 is negative 9, and negative 9 squared is 81. And so CD also simplifies to the square root of 90, which is equal to 3 root 10. So since they have the same length, we can go ahead and say that segment AB is congruent to segment CD. So because we know they're equal by the distance formula, we know that they are congruent through the definition of congruence. Okay, so that's everything that I should expect to see for an example like that. So the setup of your problem, the simplification of your problem, you might not need to show all of those steps, but you should show some of them. And then you need to finish with saying that they are congruent in a congruency statement. Okay. Example number 2, I expect that this one's going to take a couple of minutes, so just hang with me if you want to go through this. So it says J, which has coordinates 4p, 4, is equidistant from K, 3p, 12, and N, 4p, negative 13. So remember that equidistant means that J is the same distance from K and the same distance from N. If J is in quadrant 2, find the slope of JK. Okay, so we're being asked to find the slope. So change in y over change in x. Okay, but we need to know what the coordinates of JK are. So in order to know what the coordinates of JK are, we really need to know, so in order to find slope of JK, we need to know those coordinates. And those coordinates have a variable in them, so we can't just find the slope with a variable in it. So we need to solve for p. So we know that we've got these two segments, JK and JN, and they're congruent because J is equidistant to both K and N. So somewhere in the coordinate plane, we have some point J that's in quadrant 2. It's at 4p, 4. Okay, so we don't really know, but it's in quadrant 2 and it's up 4. And K is at 3p, 12. And again, we don't know if what quadrant K is in, but maybe it's, well, it should be in the same quadrant as J. So maybe K is up here. And then we've got N is at 4p, negative 12. So maybe it's down here. Okay, so it might look something like that. And we know that these two segments are congruent, okay? Well, if they're congruent, then the distance of JK and JN is equal. So what we're going to do is we're going to write an equation for the distance of JK. So JK, in terms of distance, is the change in x's. So that would be 4p minus 3p, y squared, plus the change in y's. 4 minus 12 quantity squared. And if we simplify this, 4 p's minus 3 p's is 1p, and a p squared is a p squared, plus 4 minus 12 is negative 8, and negative 8 squared is a positive 64. Now, you might be tempted to simplify that, but remember that you cannot because of this plus sign. Okay, so even though those are two perfect squares, p squared and 64, and they each could simplify, you can't because they have to be added together, and then that's not necessarily a perfect square. So that's it. That's as far as that goes. Don't take a square root of a sum or a difference, okay? All right, so then we're going to write an equation for the length of JN. So for JN, we're going to subtract our x coordinates again. So 4p minus 4p, y squared, plus 4 minus negative 13 squared. And we're going to simplify this. So 4p minus 4p is 0, and 0 squared is 0. And 4 minus negative 13 becomes 4 plus 13, which is 17. And 17 squared is 289. Okay, Now go back to the beginning. Remember that JK is congruent to JN. So now what we're going to do is take our two equations and we are going to substitute them and set them equal to each other. So we're going to say the square root of p squared plus 64 equals the square root of 289. And to solve an equation with squares in it, with square roots in it, we're going to square both sides. And we're going to get an equation now that is p squared plus 64 equals 289. And we're going to solve for p. Remember, that's our goal so that we'll be able to find the slope. So this process is pretty lengthy, but 289 minus 64 is 225, and p squared is equal to 225. So to solve for p, we're going to take the square root, and we get p is equal to plus or minus 15. Okay, so don't forget that plus or minus. If you take the square root, you have to consider both of them. Okay, so we found p, except that p has two possible answers. It's positive 15 or negative 15. Now, if you go back here, it said that j was in quadrant 2. So we know that p has to be equal to just negative 15. Okay, so if we plug in a negative 15, now our coordinates for j are 4 times negative 15, comma 4, and our coordinate for k, because we want to find the slope of jk, is 3 times negative 15, comma 12. And so our coordinates, I'm going to switch colors since I've kind of switched ideas here, is j is at negative 64, and k is at negative 45, 12. Now remember, our original question was find the slope of jk. So now that we know the coordinates of jk, we can find the slope of jk by finding the change in y over the change in x. And we get that the change in y is 4 minus 12 over negative 60 minus negative 45. And when we simplify this, running out of space here, I'll give myself a little bit of space. When we simplify this, the slope of jk is equal to negative 8. Remember, this becomes a positive over negative 15. And the slope of jk for our final answer is a positive 8/15. And there it is. Okay, so I think we derived the distance formula again, and we took a look at a pretty straightforward application with example 1, and then this definitely more challenging example 2, which you will see both types of problems in your homework. All right, have a great day. I'll talk to you later. Bye.